Table 1 shows some electrode half equations and their standard electrode potentials. Before we tackle this question, let me draw on the table. So the most negative, which is down here, goes in the direction where it loses electrons. And oxidation is the loss of electrons, which means these are reducing agents. I'm going to put a little box around here. So everything on the right is a reducing agent, but the best of this is at the bottom. And then if I change colour, so at the top of the table then, so these want to go this way, so these want to gain electrons because they're most positive. The gaining of electrons is reduction, which means that these are oxidizing agents. And the top left of this table, the bit in the green box here, okay, so deduce the oxidation state of sulfur in SO42-, so oxygen is -2 each, so that's -8, but 2 of those minuses are here, which means that the sulfur must be +6. Part B, state the weakest reducing agent in the table. So this is the best reducing agent at the bottom, that's the iron here, which means the chloride up here must be the weakest, so chloride. Write an overall equation for the reaction occurring with a cell EMF of 0.43. So we're looking at the differences between the EMFs, and it's a bit of trial and error, but you will get to these. So the difference between those two is 0.43. So the one at the top is going to go from left to right. So that's not really going on there very easily. So that one is going to go that way. And the one on the bottom, the copper, is going to go in the opposite direction. Okay. So the one on the top, the iron, has got 1 electron, so I need to times that one by 2. So let me do the iron first, going from left to right. So 2 Fe3+ goes to 2 Fe2+, and then the copper, so going from right to left, so copper plus copper 2+. The conventional representation for a cell is this. So this one is the most positive, remember, and E0 is equal to right minus the left. So I'm trying to work out the left, so E left is equal to E right minus E0. So the iron, which is in the table, is 0.77. So 0.77 minus, and we're told it's 1.02, which gives us a value of minus 0.25 volts. The EMF of an alkaline hydrogen-oxygen fuel cell is 1.23 volts. The standard electrode potential for one of the electrodes in the alkaline hydrogen-oxygen fuel cell is this. So that is one of them, but we know that the overall equation is going to be that. So what I need to do is, remember, it's this plus one that I'm going to write here added together and then cancelling it all out, that gives me this one up here. So I'm just going to cross cancel what's here. So I've got hydrogen there, I've got a water here, which will get rid of one of those waters there, and what I'm left with is going to be my other half equation. So I'm left with water plus 2E minus plus a half O2, which goes to 2OH minus. Now, obviously, you can have multiples of this. You can have 2 waters, 4 electrons, 1 oxygen, and 4 hydroxides. Okay, all of those will be the same. Calculate its standard electrode. So, okay, we've got an overall of that, and we've got this. So, the overall for this electrode then is going to have to be plus 0.4 volts. Suggest why the EMF values of the acidic and alkaline hydrogen-oxygen fuel cells are the same. It's because they have the same overall reaction. The exam board's pretty strict on that. They've underlined overall, which means you have to have that.